of our first morning speaker, Núria Fagella from University of Barcelona. She's a professor at University of Barcelona, collaborator of of Warsaw Dynamical System group. She has a lot of very many papers in top journals and a very nice book on quasi-conformal surgery. But today's talk is not going to be about quasi-conformal surgery. Its title is Structural Stability in Complex Analytic Systems.
Hello? Hello? Yes? Is it working? Yes? So, sorry? Yes. Good. So, good morning, everybody. Thank you very much, the organizers, for allowing me to give this talk, but also to all of you who, after yesterday's party and the vodka and the late hours, you were so kind to come and listen to it. So, welcome and thank you. And I hope that this will be reasonably interesting for you, because I have tried to make it so that we all can get something out of it, we all can understand a little bit, at least during some time, right? And even the specialists maybe can have also access to some new results. So the title is Structural Stability in Complex Analytic Systems in Holomorphic Dynamics, which is my field. This is, after a certain point, this is joint work with Mathieu Asterk and Anna Miriam Benini from University of Orleans and University of Parma. Those are my collaborators on this. Although this will come very much at the end, because what I would like to do today is to introduce you to how does one work with structural stability in the world of holomorphic dynamics. So let me start saying that this is about discrete dynamical systems, so that we iterate a certain map from a topology. This is very general. We will go to the holomorphic world in a second, but this is much more general in the sense that I want to talk about structural stability in general, or at least in this context. So if you have a map, let's say at least continuous, which can be seen as the evolution law of a system of observables that change with time, right? Discrete time. So every initial condition, x naught in this space X gives rise to a forward orbit, which is the result of applying repeatedly, iterating the map F to the previous one. So this is the difference equation, xn equals f of x n minus 1. And of course, we could be maybe having different equations that depend on more variables than just the past one, but that just would be reduced to this case by increasing the dimension of x. So this is fairly general, or at least this is what the type of dynamical system I will be concentrating on. So orbits, as you probably know or see easily, may have different behaviors, many different behaviors. Could be periodic, so returning to themselves, this is a sequence, or they could converge to a periodic orbit, right? Converge in the sense of approaching this orbit so that we have several subsequences that converge to each of the points of the periodic orbit, or maybe they converge to the boundary of the space. So if this is the complex plane, they could be converging to infinity or the real line, or they could behave chaotically and fill everything up, or they could do anything that you can imagine, right? So this discrete dynamical system, this very, very general setting that I wrote here, can be used to model infinitely many phenomena. You just name it, right? So population of species, so biological mathematics, financial investments, physical phenomena of all types, epidemics, we've seen many of these. So this is a very wide framework that fits into many applications and many models of reality. So the goal from the dynamical systems point of view is obviously not to solve this, not to find the sequence of points in terms of n, but, well, basically because this is usually impossible, but to understand the qualitative properties of the system, right? So for us, for example, think of z squared. So the map is f of z equals z squared on the complex plane. Everything inside the unit disk will decrease in modulus towards the fixed point 0, and everything outside the unit circle will increase in modulus towards infinity. So this would be the phase space of our dynamical system with a basin of attraction of the fixed point 0 and the basin of attraction of infinity out there. And the boundary, the circle, here we have the doubling map, the angle doubling map, and orbits in here are chaotic. Periodic orbits are dense on, periodic orbits are dense in this dynamical, in this unit circle. So here is where we see all the chaos occurring on this very simple system. But what I want to say with this slide is that I don't care if it's z squared or if it's z squared plus epsilon, in which basically you have the same behavior qualitatively. So you have a fixed point which is not 0 any longer. I have a basin of attraction of this fixed point which is not a disk anymore. I have a fractal curve as the boundary of this basin of attraction, so that's clearly not the unit circle, but still I have one attracting fixed point inside, infinity out there attracting all these outside orbits. So for me, these are the same dynamical system, okay? And let me formalize this concept for a second. So qualitatively, these two are the same, and this leads me to the concept of conjugacy. So how do I formalize the concept of being the same? What I mean is that conjugacies, which is kind of a change of variable in both ends, however. So we say that two dynamical systems, F1 and F2, from two different spaces, maybe, I don't know, they are topologically conjugate if there is an homeomorphism from one of the phase spaces to the other, such that this diagram commutes. So it's the same that applying the first dynamical system and then H, then first doing H and then F2. This is the concept of topological conjugacy. The word topological is an adjective, which means that H is continuous. At least it's a homeomorphism actually, but you could change this adjective and put CR, put linear, put conformal, put quasi-conformal, right? If you can choose H to be any of these in these regularity classes, then this conjugacy is stronger. So you require more and more things from F1 are inherited to F2. In particular and in general, even from the continuous point of view, why are conjugacies important from dynamics? Well, because if you concatenate these commutative diagrams, you will see that orbits go to orbits. Attracting periodic points go to, periodic points go to periodic points. Attracting periodic points go to attracting periodic points. Repelling also. So all the dynamical properties, qualitative properties of your system F1 are transported to the system F2. So the two phase portraits look alike, like for example these two. So this is a little bit of a more elaborate example than z squared, but at the end of the day, it's the same thing. So here we see z squared plus a certain number, which gives you a period 5 periodic orbit. These are these 5 points that you see here. So this point goes here. No, actually, it goes with rotation number 2/5, right? And but anyway, this is a period 5 periodic orbit which attracts all the yellow orbits that you see in this picture. Okay, so this is the complex plane, and we have this periodic orbit, which is what we call an attracting periodic orbit, because if I take any yellow point, any yellow initial condition, it will travel in these components and approach asymptotically this 5 periodic orbit that you see here. Any other of the yellow bulbs will eventually map to one of these 5 main ones, right? So the yellow stuff is the basin of attraction of this periodic orbit. As before, everything outside is composed of orbits that converge to infinity as we go along, right? Because Z square, any polynomial actually, has infinity as an attractor, as a super attractor actually. And here is the conjugated one. So this is an example of one of these conjugacies that we said. So here is Z squared plus another constant close to C0. And it turns out that these two dynamical systems maybe look different, but they are essentially the same one. Okay, so this is the concept of conjugacy. And this is the tool we use to compare dynamical systems, right? To define an equivalence class in the world that you decide to analyze. So this leads us to the concept of structural stability. Okay, so precisely, so this concept, which is very old, it's attributed, or at least the literature attributes it to Andronov and Pontryagin in 1937, but Poincaré didn't give it this name, but already talked about it, and Fatou, for sure, in the 1900s, talked about it quite explicitly. And what is this concept about? So what does it mean for a map? What does it mean for a map to be structurally stable? Well, this is a loose, not a very precise definition, because I should say where. And that's why I said in C, and C I mean a certain family or a certain class of regularity. Okay, so my map is structurally stable in the class where it lives or where I decide to embed it, if it has a neighborhood of maps in this function space such that all maps in this neighborhood are topologically conjugate to F. They belong to the same equivalence class, talking about topological conjugacies. Okay? Equivalently, if every map G in this space that I'm studying sufficiently close to F in the appropriate topology is topologically conjugate to F, and I wrote this because I want to emphasize that this conjugacy should depend continuously on the map that I'm choosing. Okay, so this is this concept of structurally stable. So somehow in the same component, let me be very imprecise here, of the equivalence class that I'm defining, all those maps would be structurally stable because they are all topologically conjugate to each other. They are also called robust for obvious reason. This kind of tells you that if I kick it, right, if I perturb it a little, if I blow, the thing moves a little, but not much, and nothing really changes. The number of equilibria is the same. The whole phase space looks similar as we saw. Okay, so they are very robust with respect to perturbations. So an example, hyperbolic maps are structurally stable. And I'm not going to define precisely what a hyperbolic map is. If you know it, that's great. If not, maybe it will come later, because this, depending where you are, it can be defined in one way or another, right? But basically, it's simply that periodic orbits have some kind of transversal, so attracting and repelling directions. Or let's say that every periodic map, every periodic point is either attracting or repelling. Although, let me please not go into this. But these are an important example of structurally stable maps. Okay, so the question that I want to address or talk about is the question of density of structurally stable maps. So somehow these are the good ones, the desirable ones, the ones that don't change under perturbations, the ones that hold that for which numerical errors are not important, right? So if I'm trying to compute it numerically and I'm structurally stable, if I make an error, it's going to be forgiving somehow, right? So those are the ones that one type of maps that is good, and therefore it's natural to ask in the class of regularity where you are working whether they are dense on this space, okay? Whether a dense set of maps in this space has this property of structural stability. Clearly, by definition, the set of structurally stable maps is always open. It's just by definition, right? Because it's a matter of finding neighborhoods. But dense is definitely a question. And this is an old question. And this is a subtle question, not an easy one, okay? It has actually employed mathematicians for a long time. So actually this was, it's a problem in Smail's list, 11th problem, except that he asked about hyperbolic maps, okay? Not about structurally stable, but soon after he kind of changed this question to structurally stable, which is simpler and more approachable than asking about hyperbolicity, density of hyperbolicity, which, as many of you know, it's a standing question nowadays still for very simple maps. Okay, so structurally stable maps are dense in many instances, and I don't want to get into these results. There's a long history. You can read about it in many, many papers. So, for example, it's true if we talk about CR maps of the interval of the circle, the key thing is dimension 1 of X, so space of dimension 1, the interval or the circle, compact spaces. But it's false, for example, in the moment that you look at dynamics or diffeomorphisms of manifolds of real dimension bigger or equal than 2, the plane, for example. Okay, so this is called this is called nowadays the Newhouse phenomena, and I don't know, I named here some names, but there are more. So basically this famous example of Smith in 66, etc. So you see, this is not a property that is true in general, very far from it, and actually it's still unanswered in many, many settings. So this is about real dynamics, and I want to talk about complex dynamics, which, as usual, is a bit in between dimension 1 and dimension 2, right? So it's this dimension 1.5 complex maps on the plane, and this is exactly what happens. So it's in the plane, but how do we understand holomorphic maps? One-dimensional, one complex dimensional holomorphic maps. So those can be either rational maps or transcendental. So what do I mean about rational? Rational is like the compact case. So X is the complex plane union infinity, the Riemann sphere, compactified to the Riemann sphere. And this is like holomorphic maps on a compact manifold of this dimension. And in this setting, the very renowned theory of Magnesat and Sullivan in 83 and independently Liebig in 84 proved that indeed structurally stable maps are open and dense. And we will go through this slowly in a moment. But let me just say that this is the compact case. So in this case, this proof was successful. However, in the transcendental case, things are a little bit different. So the transcendental maps are those with essential singularities. So that's what I call the non-compact case, because in the simplest case, you can put this essential singularity at infinity, and then you are iterating from the complex plane to itself if you are in the entire world. Or you could actually not quite be in the situation I described at the beginning. You could admit the function to have poles, so in the essential singularity to have preimages, and those are orbits that exit your dynamical system or your phase space after a certain finite number of iterations. But that's also a dynamical system in whatever points remain in your phase plane forever. Okay, so that's still, that's actually where we have been contributing to this subject. So those are the meromorphic dynamical systems, although we call them also, sorry, but this just, okay, so in the entire case, the question is also partially solved, and when I say partially, is that not in every situation, not in every class, structurally stable maps are dense. We'll go into it in a second. But if you leave the entire world, there is nothing proven, or this was like a part of this question that had not been approached before, and that's where we concentrated our work. Let me just say that this is one thing that I'm talking about, but in the moment that you go to P2, P3, so K bigger than 1, right? So the complex projective space of dimension higher than 1, so not the sphere, then density fails miserably. Okay, so it's just not. There are examples where the bifurcation locus, we'll talk about it in a second, has interior, and there are examples, and this is very recent work actually. So this is a topic that has been occupying a lot of mathematics in this field. Okay, so this is basically what remained open, but before we talk about the new stuff, let me just go a little bit slowly about why this concept of structural stability, first of all, which form it takes in holomorphic dynamics, which is a bit different, and second, let me comment on the results of rational maps, which will be probably interesting already in itself. So let me just mention that, going to what I said before, that you have to say, where are you considering your map? Where do you think your map belongs? Where are you studying structural stability? So for example, it can be studied in a variety of places, right? You could, for example, talk about structurally stable maps in the full family of rational maps of degree 3, for example, right? That's degree D. This is a manifold of dimension 2D minus 2, right? Or you could look at slices of this space, I don't know. But for example, you could look at dynamically defined slices. So for example, if you look at polynomials of degree D, that's a slice of this much bigger space, which is the full family of rational maps, right? And this is dynamically defined because you are not just taking a slice, you are taking the slice of rational maps for which infinity is omitted, no poles, right? So as you see, in these different settings, your answer to density of structural stability could be different, okay? Could be. Or another slice that makes sense, cubic polynomials with a super attracting fixed point, right? This is what I mean about dynamically defined. These are nice analytic slices of your general space. Or in transcendental dynamics, the family e to the z plus lambda, that's also a one-dimensional family. Or natural families of rational or transcendental maps. I'm not defining this, but I'm just saying that this is the setting where we work, and they could be arbitrarily high dimensional, but the property they have is that they preserve the covering properties. And what do I mean by they preserve the covering properties? Well, before I go on, I need to tell you about some important players in the world of complex dynamics. So this has nothing to do with dynamics. I'm just explaining or introducing to you what we call the singular values, which are few and discrete, but well, not always. But so a point in my complex plane may be of 3 types, right? It may be a regular point, and those are the majority. And what do I mean by that? I mean a point for which in a neighborhood every inverse branch is well defined of the map F, okay? Well defined and univalent, so I have many branches of the inverses. Obviously my map is not bijective, right? But they are all well defined in some neighborhood of my point. Critical values, think of 0 for z squared, right? If I take a neighborhood of 0, there is no square root that is well defined. That's the example of a critical value. So some branch of the inverse is not well defined because in this direction is d to 1. So that's an example. But maybe others are. So this could be a cubic polynomial, and one of them is not, but the others are. This is the example of a critical value. Obviously, this preimage is a critical point, a 0 of the derivative. or asymptotic values, which is basically the same thing, but infinitely many. This map is infinitely to 1, so this branch of the inverse is not well defined because on this direction is infinitely to 1, except for the center point. Think of 0 for the exponential. If I take a neighborhood of 0, the logarithm, right, the pre-image of this neighborhood will give me a whole left half plane with infinitely many pre-images of every point except 0, right? So this is what we call an asymptotic value. These are very special points. Okay? Points for which branches of the inverse fail to exist are very special, and they play a crucial role. For example, and just as one example of many, every attracting cycle must attract one of these singular values. So give me a map with 2 singular values, at most it will have 2 stable equilibria. Okay, so this is very particular for the complex. That's why dynamical systems in one complex dimension really, with the use of this tool, it allows you to visualize and to really understand many things. There's a lot of mathematics that can be done thanks to this property. And actually, I've been here really modest, because modest is not the word, but simplifying, because it's not only attracting cycles that need a singular value. Okay, basically every stable behavior needs a singular value to be associated to it. So singular values play a big role in determining the possible dynamics of my map. Okay, for example, this allows me to draw the famous Mandelbrot set. Why? Z squared plus C. How many? It's first of all, no asymptotic values because it's a polynomial. How many critical values? Differentiate. The derivative of Z squared plus C is 2Z. Only 1, 0, Z equals 0. So 0 is the only critical point, C is the only critical value. So that's how these pictures are made. I take, for every value of C, this is the parameter plane, I iterate my singular value, my 0, my C, and I see where it goes, and depending on what this critical orbit does, I paint it in one color or in another. And that's the picture it comes out. Trivial exercise for any high school student. Maybe he or she doesn't know what he's doing, but it's easy to draw it and much more difficult to understand it. But so basically what we see here in this color, so for example, every C in here gives me my critical orbit converging to an attracting fixed point. Every C in here to a period 2 orbit. Every C outside the Mandelbrot set, the critical orbit converges to infinity, etc. So this gives me a catalog of dynamical systems, and here I can ask, what are the equivalence classes of the structural stability equivalence relation, etc. Okay, we'll go back to this. Just other slices that you can do. Rational maps of degree 4 with a certain dynamical property, or e to the z plus lambda, this is the lambda plane. Different colors correspond to different periods of attracting periodic orbits. Or lambda tangency, this one has poles. Again, different colors correspond to different periodic orbits. Okay, this algorithm is not the same as here, where I've painted every ball with the same color. So I apologize for that. Okay, and again, this e to the z plus lambda, one singular value, so it's a one-dimensional slice. Lambda tangent z has 2 asymptotic values, but they are symmetric, so that's why, again, I can plot pictures on the one-dimensional plane. Okay, so what do we look at in here? So let me just review a little bit. How does this phase space look like? Just because these names will appear. So the complex plane splits into these totally invariant, totally separated sets, the Fatou set, which is basically all these stable components that we've seen, basins of attraction, rotation disks, etc., right? And this is open, that corresponds to the iterates forming a normal or a continuous family. But then the Julia set is the complement, which is that black part. So let's look at this picture, for example. All the yellow and all the red is the Fatou set. basis of attraction of infinity, rotation domain here, right? Every yellow orbit does the same as their neighbors. Every red orbit also, because they all go to infinity. The boundary is the Julia set, where chaos occurs. Think of Z squared. The picture you saw of the circle is repeated for every polynomial, except that the boundary is a fractal, not a circle. Okay, that's where the repelling periodic points are dense on this boundary, on this Julia set. That's the boundary between the different stable behaviors, so it supports the tension of orbits wanting to do different things, and they have to stay put because they cannot decide where to go. Or in the transcendental world, much more complicated, right? Unbounded Julia sets, but nevertheless, same dynamical partition, okay? So that's the objects we look at. And now let me tell you what are the peculiarities of this concept of structural stability in complex dynamics. So let me just say that I've been cheating, I've been talking to you about structural stability, which is the easier concept to define and the one that we are most familiar with in dynamics. But really, when we are doing holomorphic dynamics, we talk about the closely related concept, which is much more natural in this setting. I will not get into why, but really what we look at is what we call J stability, which is very easy to understand. It's simply the same concept except only on the Julia set. Basically, the idea is that we only look at whether the Julia set behaves in this stable way, okay? So that's more natural in this setting and closely related. And let me now give you a precise definition of J stability. So first of all, let me introduce you to this concept of a holomorphic motion, which is simply things that move holomorphically, as the name indicates, right? A holomorphic motion of a set, and this set could be 3 points, okay, is simply a map from, so it's a holomorphic motion over some set of parameters, right? So I move E with respect to lambda. E is my set in the complex plane, U is my set of parameters, an open set of parameters. So I will say that E moves holomorphically with respect to lambda if I have this two-variable map, right? Lambda z goes to h lambda of z, and you should basically think, and the conditions, excuse me, is that for my center point, I'm just the identity. On the variable, I only require it to be injective, and on the parameter, I require it to be holomorphic. Okay, so 3 points that move holomorphically with respect to my parameter and never collide, that's a holomorphic motion. Okay? Now, J stability tells you, the definition of J stability is my map will be J stable if I can move the Julia set holomorphically. Okay? If my Julia set moves, but in a very smooth way, so holomorphically with respect to the parameter, and always injectively with respect to the point. So no collisions, no identifications, right? It preserves its shape all the time. And this holomorphic motion preserves the dynamics. That's the conjugacy. This is the conjugacy with among all the functions on this parameter neighborhood. That's the conjugacy, which here observe that depends actually holomorphically on lambda. Okay, so this is the same concept that I was talking about to you, is the same, except we look at it on the Julia set and in fact on a neighborhood. That will be J stability, which is the concept of structure stability adapted to the naturality of holomorphic dynamics. Now, give me a holomorphic family of maps, give me a slice, give me a family, as many parameters as you want in a complex connected manifold. The stability locus will be those maps that are J stable, and the bifurcation locus will be the set of maps for which that they are not J stable, so where bifurcations occur. Okay, that's the bifurcation locus, and obviously this is and the question of density would be to ask whether this set of J stable parameters is dense. Open is automatic, but whether it's dense, which is the same as asking whether the bifurcation locus has empty interior. Okay, so here is the first example. All the boundary of the Mandelbrot set is precisely the bifurcation locus of the family Z squared plus C. So bifurcations occur when we go from each of these components to the next, when we cross the boundary of them all from the inside to the outside. That's the bifurcation locus. And because of the Mañé-Sullivan theorem, this bifurcation locus has empty interior, which is the same as saying that structurally stable maps are dense, or J-stable maps are dense in this picture. And this boundary, which here looks very thin, but in reality has Hausdorff dimension 2, so it's very thick, right? But still, it has no interior, and well, at least the bifurcation locus has no interior, sorry, and not yet known whether it has positive measure or not. Okay, and this is the famous Mandelbrot set. Many conjectures are still, or some very important conjectures are still open about this very simple set. Okay, so so let me give you the magic tool that relates the question of J stability with the question with periodic orbits. Okay, so J stability, the key relation which happens in holomorphic dynamics is this lambda lemma. The lambda lemma, which was the key result in the Mañé-Sullivan paper, or one of the key results, says the following. Give me a set, any set, which moves holomorphically with your parameter. Well, this holomorphic motion can be extended to the closure. That's it. But not only that, when you extend it to the closure, the resulting holomorphic motion of the closure will be jointly continuous. Remember that for a holomorphic motion, we didn't ask about continuity. We only asked about injectivity with respect to Z, right? And holomorphicity with respect to the parameter. This tells you the result will be jointly continuous, and not only that, it will be quasi-conformal. If you don't know what this is, ignore it, okay? So this is, I would say, very powerful, almost magic, and look at what gives you in dynamics. It says, well, since we know that the Julia set is the closure of the repelling periodic points, right? This is one of the properties I said, then it would be enough to have a holomorphic motion of the repelling periodic points, since I could extend it to the closure and the conjugacy would be preserved just by continuity. Having a holomorphic motion of my repelling periodic points would be enough to have a holomorphic motion of the Julia set, which means J stability. So being J stable on a parameter's neighborhood is equivalent to having simply a holomorphic motion of periodic points, nothing else. And this is algebraic already, right? Because what does it mean that periodic points can be moved with the parameter with no collision? This means that they can be, that you can apply the implicit function theorem to them, simply. So this is exactly what you have when you don't have periodic orbits of multiplier equal to 1, which is the only one that makes the implicit function theorem fail. So this is really, excuse me, this is really the key property, right? So this lambda lemma reduces your problem of J stability to the existence or non-existence of parabolic periodic points for maps on your on the neighborhood of your center function, right? So J stability is equivalent to not having collisions of your periodic orbits when you move lambda in the neighborhood. This is what happens in rational maps, right? So actually much more than this is true, and the Mañé-Sullivan theorem, tells you more properties, not only this one, but many more properties that are equivalent to J stability. So this is the two first are the ones that we just said. A map is J stable in the whole, so maps in U are J stable, even only if there is no parabolic cycles. Forget about persistence for a moment. There are no parabolic cycles there are no maps with parabolic periodic points in the neighborhood U. But also, no attracting cycles are born or die in this neighborhood, which is kind of saying no bifurcations, right? And something new that I haven't talked about, but I told you critical values or singular values are really important. Indeed, here they also have a role to play. And basically it's telling you that in order to have these bifurcations, you need critical values changing behavior. So it's equivalent, J stability is equivalent to having the critical values to be passive, which means that for all parameters in this neighborhood U, critical values do behave in the same way, which is equivalent to say that the sequence of maps, the iterates of the critical values, are behaving in a normal or equicontinuous way, okay? So that they don't change behavior while in your set U. So this was the celebrated Mañez-Sullivan theorem, right? As I say, very based in Ganga lemma, hard work to make all these proofs work, right? And the corollary, which is not immediate, it's not difficult, but it's not completely obvious from here, is that J stable form an open and dense set of J stable parameters form an open dense set in the manifold M where I'm studying my family, okay? Or equivalently, that the bifurcation locus of the family, arbitrary family that I've taken here, is empty. Okay, so so this is what was done for rational maps. And now let me just give a brief account of what is our contribution for non-rational maps. So maps with essential singularity, so the non-compact case. So we look at maps from the complex plane to maybe the Riemann sphere. Infinity is an essential singularity. Again, M is just a complex manifold. Still true that Julia said is the closure of the repelling periodic points. That has not changed. So still true that J stability is equivalent to holomorphic motion of periodic orbits. Same. Okay, so again, I have to worry about the holomorphic motion when my periodic cycles move holomorphically with the parameter. Still true that if they do, no collisions are possible, so no parabolic cycles can exist for maps in my neighborhood. Still true. However, the reverse is not true any longer, because having no collisions of periodic orbits does not guarantee that your periodic orbit remains in the phase space and is repelling, or whatever, it preserves its character. Because as opposed to the rational case where the sphere is a compact space and there's nowhere to go, right? When you live in the complex plane, there is somewhere to go. My periodic orbit could be simply disappearing to infinity without changing its multiplier, without changing its character. So in order to disappear, doesn't need to collapse with anybody. It could simply go, and it's not there anymore, because C has a way of escaping towards the essential singularity. So this is a new type of bifurcation that is happening in this setting of the non-compact manifold, which does not happen in rational maps when you work on the Riemann sphere. So periodic points could be disappearing to infinity even while they are attracting or while they are repelling. Okay, so no parabolics involved at all. So this is a new type of phenomena, a new type of bifurcation, and this means that the arguments in the Mañez-Sullivan equivalencies do not work in this setting. Right? right? So this is just a formal definition of what I just said. What does it mean to disappear to infinity? But I think I've described it, so let me jump over this. And just let me give you an example. Z plus lambda plus e to the z. So compute the fixed points. Equals z, it's e to the z plus lambda equals 0, right? So how many fixed points? Infinitely many, as long as lambda is not 0, right? So I have infinitely many fixed points for every lambda, but when lambda converges to lambda equals 0, which is a perfectly fine parameter for this family, all these fixed points are gone. No fixed points for the map. Okay, so these fixed points have not changed character, they simply left. Okay, so lambda 0 equals 0 would be an example of this type of bifurcation that I'm talking about. Another one more meaningful, I'll tell you why in a second, is the tangent z. So I have a period 2 orbit, this one goes here and this one goes back, and as I move the parameter, one of these members of the period 2 orbit, which is moving nicely with the implicit function theorem, but one of them is approaching a pole, is going towards pi over 2, so its image is every time further. When lambda is pi over 2, pi I over 2, one of the periodic orbits is the pole, and the image is infinity, so the cycle is gone. Okay? This phenomenon is not new. It has been observed by Janina Kotus and Linda Kim in several works over the times for particular families like the tangent map, like exactly this one I gave here, also in more generality. So there are several observations of this phenomena, and what we add in the work I'm presenting is a deep study of this phenomena in complete generality. Okay? So just let me, for those that like pictures in several dimensions, well, it's obviously not in several dimensions, but let me just draw my space M cross C, and you could formalize this phenomenon by saying that if I consider these analytic surfaces, which are pairs of lambda z, for which z is a periodic point of period n, or a fixed point of f to the n, then as I move lambda, these are analytic surfaces, right? So if these, for example, fixed lambda, each one of these is a point of my periodic orbit, and as long as the implicit function works and nothing happens, they move separately. So the holomorphic motion is this evolution towards there, right? Now, what could it happen? That two of these branches collapse. That's exactly a collision parabolics, right? And if you consider this, if you consider, I know it's just that the cursor is not visible, right? Well, pi 1, if you consider this projection onto the first coordinate, you see that this is precisely a singularity, because given lambda, pi 1 minus 1 is not well defined here. So this is what it would be a critical value of pi 1. But also one of these branches could just disappear to infinity. That would be a cycle disappearing to infinity, and then lambda 0 would be an asymptotic value of this pi 1 map. Okay, something for which you cannot, you find all the pre-images at infinity. And these are really the two obstructions to J stability. The first one is already present in rational maps. The second one is the new one appearing in transcendental dynamics. And what are the questions that we try to address? It's like, okay, so how does this new type of bifurcation relate to the poles, relate to the singular values, relate to the parabolic cycles? If it does, can this occur out of the blue? When does this occur? When do these bifurcations happen? So do they respond to some algebraic equation like parabolic cycles? Existing parabolic cycles is the solution of an algebraic equation. What about these? Where are they located, right? Well, we shall not answer the questions, or at least not, well, what we do is to look at this in the setting of finite type maps, so only finitely many singular values, and also natural families, which means preserving the covering properties. Let me not get into this. Let me just say that Eremenko and Lewitt already solved the entire case, saying not that this bifurcation doesn't matter, but saying this bifurcation does not occur when the map is entire. Okay, so basically what they proved, a very involved paper, is that you don't have to worry about this bifurcation for entire maps. Okay, in other words, so basically, since this does not occur, Magnez-Sullivan goes through structural stability set is dense in families of entire functions of finite. Conclusion: if cycles have to disappear to infinity, if this bifurcation has to occur, we need poles, and that's the setting that we work on. Even further, at least one pole that is not omitted, but let's not get into that. And in this setting, the bifurcation does occur. For example, we saw it in the tangent example. And let me just say that that means that all the proofs break. And nevertheless, our result, which I will not get into it, but I will tell you just 2 words about what we use, is that Magnez-Sullivan can still be recovered with a totally different set of arguments. Okay, so in the same setting as the rational map, so if you have a natural family of meromorphic maps with a finite number of singular values, then J stability is equivalent to passivity of singular values, is equivalent to no bifurcations between attracting cycles, it's equivalent to non-existence of parabolic cycles in a neighborhood. So the same result goes through. The corollary, therefore, is that structurally stable dynamics, J-stable dynamics in this setting are also open and dense. And just to finish, let me say that the set of techniques and concepts that you need is different, right? Because to relate all these concepts, you need to use the understanding of this type of bifurcation in detail and in generality. So you need to talk about virtual cycles, you need to talk about solutions of some equations where the critical value, the singular values map to poles, that's the relation with the algebraic or the not algebraic, the transcendental equations. You need to do an accurate analysis of the activity and passivity of singular values in relation to all these that we mentioned. You need to prove some density theorems on the bifurcation locus or the activity locus, multiple tools, etc. And I will finish here. Thank you very much for your attention.
Thank you, Núria, for your inspiring talk. And now there is time for questions and comments and remarks. No, they seem to be postponed for the coffee break. So let's thank the speaker again.